Alright guys, here we go. So we are looking at, you could say day 3 of Unit 8. And we're introducing the same idea but with two different representations. We are finding the volumes of things that are rotating about an axis. Okay? And it's called the disk method. And it's called the solids of revolution with the washer method. Alright, so what I want you to visualize is on this first one, as I rotate it, you can see that from the right side, there's a bunch of circles. So these circles, so here's that X and here's that Y axis. This is from the side view. You're looking at it straight from up top. And if I wanted you to take a slice somewhere in the middle, that would probably appear just like that, like a line. So this is, believe it or not, a slice that I just took. And can you tell me what shape this slice is? Circle. It's a circle. Because if I turn it sideways, you see that slice. And if I go through this, you see it change depending upon where it's at. The radius is getting smaller or bigger, so on and so forth. Okay? So the radius is just the distance between that function, f of x, which in this particular instance is this one right here, and the x-axis. That right there is showing you the length of the radius. And notice how it's variegated. It changes depending upon where that y value between the x-axis and the function lie. You with me? Any questions before we start integrating this one? Okay, so let's look at how could we find the area, or sorry, the volume equation for this cross section. Okay, so if I'm going to integrate, and we saw this last class, if we integrate something that represents area, what would it yield? Volume. Okay, and we could do it like dx are vertical slices. And when I mean vertical slices, I'm talking about like this vertical slice right here that we just took. This right here is a dx. Because there's a lot of these vertical slices of these circles that are all stacked on top. If it's ay, it would be dy. It still yields volume, but in this case it's going to be the horizontal slices. And that's a little bit different, okay? It's still very, very close to this radius that I highlighted here as far as this blue f of x. The only difference is, instead of it being a blue f of x, it's going to be a sideways f of y. You with me? So let's say that I had a picture that looked like this. I had a picture that looked like this, and the shaded region was here, and I asked you to take a horizontal slice. It would be this right here. Okay? So let's pretend that this blue function right here is a piece of y is equal to negative x squared plus, I don't know, 10. This would be 10. Let's do it a little bit easier. Instead of plus 10, I'll do plus 9. So if I do plus 9, this y value is 9. 0, 9 is that point. Go with me? What would this point be at the x-intercept? 3, 0. Because in the equation, that's when it would satisfy of being the 0 as the y value. Go with me? So for this one, if they were horizontal slices just like this, I would have from what to what? From A, well, in this case, they're going to be C to D. It's going to be the y values. From 0 to what? 9. Go with me? So I'm looking at the y values.
Well, since it's a horizontal.
If I'm doing horizontal. Let me get to that in just a bit. Okay, let me back up a little bit and do the easier one. Let's do vertical slices. So if I'm doing vertical slices, it would be from 0 to what? 3. Dx or dy? Dx, because they're vertical slices. You with me? And now it would be the top minus the bottom. The top is this function. So if I did top minus the bottom, can you tell me what the bottom function is? Y equals 0, right? So notice that I solved for y. This is this height per se, like it is over here. It's like that for this particular equation. If you solve for y and get it all by itself, you have this piece written in terms of x, because you're ready to take it, the integral, in respect to x. Okay, so let's go back to this red one now. So I'm telling you, let's take now a horizontal slice. And all we're doing is area right now, okay? What would be the top? Would it still be this function?
No, it's going to be x equals 0, or 3.
So here we go. Do you agree that this equation right here, this x, negative x squared plus 9, do you agree that this represents this piece right here? Yeah. So now if I want to know this red horizontal distance, I have to solve this equation for x. You with me? So let's add this over here. Let's subtract the y. And let's take the square root. Technically it's the plus and minus version of that. But the positive one is over here on the right. The negative one would be on the left. So what I'm just looking at really is just this positive root. Let me highlight it for you. This in green, whoops, is the length, the horizontal length right here. You with me? So now if I looked at this, the top minus the bottom, it would be over here in red, the root of 9 minus y minus x equals 0. Question so far? So that's pretty straightforward as far as area goes, and you guys have already done homework on this. You've got some good practice on it. But now we're going to move this on to integrating three-dimensional three-dimensional volumes, creating these three-dimensional volumes. Okay? So let's go ahead and look at this one in particular. This disk method. Here we go. What would you say is step 1?
Find the shape of the
Okay, yep. Find the shape of each slice. And on this one, the shape of each slice is going to be a what?
circle.
A circle. So the area is pi r squared. This is the disk method. Okay? So in this integral, the pi can come out, the r will stay inside, and this one in particular, vertical slices, is going to be what?
Or dx.
Dx, yeah, dx for vertical slices. You with me? All right, so here we go. I need to solve for y, which conveniently they have already done for us. So whatever this f of x is, that's the function that's going to represent any given height, which in this case is the radius, highlighted in blue, of each independent circle. You with me? From what to what? What are the bounds? A to B. That right there will give you the volume. You good? Now, what's different over here is this is called the washer method. And the reason why it's called a washer method is it's in the shape of a washer. not like a washer and dryer that you're used to seeing, but it's in the shape of a washer. And a washer looks like this. Looks like a donut, but it's a nice flat piece of metal, if you will. Okay? So looking at this, what it will create is something over here. Now look, this region 1 right here, we're about to rotate about this axis of y equals -1. Guys, this right here is y equals -1. And what I'm about to do is I'm going to rotate this shaded region. This is just like one slice. And I'm going to rotate it and pull it out of the page around 360 degrees. And I'm going to spin it around y is equal to -1. Here we go. So you see it going all the way, and it creates that shape. If I don't make it translucent, you can't see the axes. But it is a three-dimensional volume. And you see from the side it has void in it. It has a big old huge hole gap. Let me make it translucent again so you can see it in the middle. Okay? If I had a different function, let's say that I had that function but still rotating it about y is equal to -1, you notice that the change in the figure, the volume, is a little bit different, but nonetheless, it still has void in the middle. You can go all the way around. You see that? Okay? So because of the fact that it has a gap of some kind, and the reason why it has a gap, the number one reason why it has a gap, is because between this axis of rotation and that shaded region, there is some parts that are not filled in with matter. You see what I'm saying? Because if they were filled in with matter and it was a solid area, it would be a solid, just like over here on the disk method. Yes, Nate?
I was wondering, what if you have an equation that crosses over the axis of rotation? Does the overlap just the same as...
Okay, so that's cool. You will not have something that difficult. You have to reprioritize or partition these integrals to make that work. Okay? But you won't have something like that. Yours are easier, much easier rotations. Okay? But awesome question. Yes?
I had a different question on the previous one.
The disk one?
Yeah.
Okay.
Can you write like f of x squared? Like can you put the square like in between the f and the x?
Oh, you can, but the thing is that you're not going to put f of x. Like you're going to have actual equations that you'll see that we're going to build together here in just a bit. Okay? Any questions out there? Yeah.
What would the washer method, like the...
Oh, what would the equation be? Okay, here we go. So, can someone tell me what is the area of this entire circle? Pi r squared. What is the area of this smaller circle? Little pi r squared. And if I subtract it, all I end up having left over is just what's in between area. You with me? It's like the big one, subtract the small one, it's like knocking it out. That is the cross section that's left.
So then for the integral, you could take out pi.
And there you go. So let's GCF out this pi. Okay, so I'll put that down here. And for this particular one, we're going to say it's like what? Let's say 0 to 6.5 for this specific one, because that's where the x is at. And it's going to be the top minus the bottom. It's going to be the bigger R minus the smaller r. Okay? So here we go. Watch this. Let's call this graph right here. Nate, this kind of goes with what you were asking. Let's call this f of x. And let's call this one down here, let's call that g of x. Ready? This is where people get confused. And it is a little bit weird to look at. First of all, is it dx or dy?
dx.
Dx. So the integral dx. Now we got to come up with something that shows big R squared minus little r squared. So in green, I'm going to show you big R. And I'm going to show you big R from its center of rotation. So I think you should grab your pencil, whatever, and from the axis of rotation, which in this case is y equals -1, pick something in the middle and go to the furthest outer piece of that shaded region. Because what you just did, and I'll do it over here, is you went and created that. That's big R. Y'all with me? So looking at this, that's big R. Let's now create something that represents, instead of going all the way up, oops, we're just going to stop where I can show you little r. Which here would look like that.
Can you draw that? Oh, it's just to the most
To the
bottom.
blue one, yeah.
Gotcha.
You with me? But you notice I'm always starting from the axis of symmetry, or sorry, the axis of rotation, and then I go to the shaded region. Now, what is? Let's look at the black one, the big R. What is the top function right here of big R? F of x. So that's the top. Minus the bottom. What's the bottom function of that big R? -1. The bottom piece is way down here. It's like the endpoints of this radius. So it will be minus a -1, which some of you are seeing. Well, it's the same as adding 1. You could do that, or just subtract it. So f of x minus -1. That is big R squared. Okay, so let's go over here to little r squared. Little r squared is from the axis of revolution to the nearest function, which in this case is g of x. What's the top of that red line? G of x. So you have g of x minus, okay, so I'll color coordinate it, minus what? -1. You with me? Now this will give you the volume exactly of this picture without having to put it in water and submerge it and find the volume that way. You with me? Questions?
Mike, I have a question that's different. It's about the disk method.
Okay.
So you remember when you said when we were doing dy, we have to like turn our head
Yep.
to find, is that just to find the top function versus the bottom function?
That's only for top minus bottom. You don't turn your head
Bounds.
for the bounds. You don't turn your head for the bounds. You go from bottom or lowest y value up to the highest y value.
Gotcha.
And we're going to do some of that together here in just a bit. Any questions before we keep going? These visuals should help big time, because otherwise this is kind of out there to figure it out by just trying to visualize it in your head. Now remember, we're doing these cross sections. Look at this. So for instance, what we've recently finished kind of looking at were these cross sections of perpendicular to the x-axis or perpendicular to the y-axis. So let's say right here, here's my x And then right here for 0, here's my y. Sorry, my bad. This is my x, this is my y axis. And then you've learned recently that a z axis kind of came up like that. You guys see it?
Yeah.
So looking at this, I have two functions. I can look at f of x, could be this one. Maybe that was a little bit too big. And then I can look at g of x being maybe this one. And the region that's shaded in between them is this region right here. Good, right? So that's the base. This is what we were talking about. I just want you to visualize it more. The cross sections of this volume are triangles, semicircles, circles, which creates this sphere kind of looking thing. Okay? Squares. So there's big squares in the middle, smaller squares at the edge, but all the while it still has that base. That's the region between two of those functions. Rectangles. Okay, if I told you to take a slice of the center rectangle, just so that you are aware, it would probably look something like this, kind of all the way here, and up. That would be like the one right in the center. Okay, I'm just trying to help you visualize this because that's the hardest part, is visualizing it. Okay? Alright, so now let's move on and let's go to, in our notes, we have, let me pull them up, a couple of example problems, and then I do have something for you to do at the end of class that not only revolves around doing work on the boards, like presentation boards, but also we are going to write a paragraph of all the steps of how to solve a problem that I give you. So you're going to write it in a paragraph. You're not going to list it like bullet points. You're going to write it in a paragraph because I want you to truly know the steps and details. It's almost like remember when we did related rates and it was like dreads? And it was like diagram, rates, equation, derivatives, and so on and so forth. We're doing that at the end of class today. Alright, so let's go ahead and pull this up. Oops. Alright, so we're looking at disc and washer method, volumes. And the first one we'll start is right here. Alright, so let me go ahead and start another video.